when we look at this picture, which is a very, very limited picture of the action, there are a lot of questions that come up, and people have been asking lots of questions about this. But we're trying to really sort of take 20 steps back from the details of the Earth's magnetosphere and think of it in a global sense to compare it really with the alternative paradigm, which is you're not driving convective flow through this Dungy cycle of reconnection, but you're driving primarily your flow is rotation with the planet. And so that if you have a magnetic field going out to some plasma out here, and you are coupled with filter line currents to the ionosphere, and if the ionosphere is rigorously coupled to the atmosphere, more about that later in the week or this afternoon, then you will end up with plasma out here that rotate with the planetary atmosphere. And one assumes that that is the planetary rotation of the planet. And so then comes the question, if you have a situation where that's the case, what do the flows look like in the magnetosphere? Well, obviously, you'll have a co-rotation flow, which is just omega cross r. And you can then compare that with this convective solar wind-driven convection system that is driven by some reconnection efficiency squiggle. I always forget which squiggle that is. Which squiggle is that? So, zeta? Okay, thank you. Squiggle times V solar wind and this convection flows, which vary, get stronger as you get towards the magnetopause. Okay, and so then you can derive a fraction of the magnetosphere that is dominated by rotation, okay? And we can compare that with the size of the magnetopause. And we can then do this, we take the size of the plasma pores, traditionally that's been called the plasma pores because at Earth, inside that region, we have a dense plasma that comes from the Earth's ionosphere, fills up that region, and it was observed that outside the density suddenly dropped off, and so that was the pause, the boundary between a lot of plasma and very little plasma. And that we can describe where that plasma pause is as it compared to the size of the magnetosphere by just working out where these things equate. And you end up with an approximate description that basically you can follow through the algebra. Okay, my computer is running out of power. Could I've got it. My no, sorry. I've got one. I've got one in the back here. Sorry, I just suddenly realized. Okay, so you end up with an expression, and I know it looks really messy, but you'll see that it is not very dependent on solar wind. 1/12 power is not a strong power. B solar wind to the 2/3. But what's really important is these two quantities, the rotation rate, obviously, and mu here, where which is the magnetic moment of the planet, which is really just B naught times the radius of the planet squared, which is just a way of saying how strong the magnetic field is of the planet. Okay, there we are. So now, if we just think about this, we have a strong magnetic field and strong rotation rate, then this will mean that the magnetosphere is dominated by rotation, and the plasma pores will be out further out. Okay, so let's do an example here. We take this situation. What would happen to the location of this plasma pores if we did this? What if we had changed the reconnection efficiency? Say we had a magnetosphere and an upstream condition where this reconnection efficiency is really strong and you're driving this Dungy flow like crazy, what would happen to this plasma pores boundary? Would it move in or would it move out? What are you doing when you change your reconnection efficiency? What are the relative importance of rotation versus solar wind-driven, reconnection-driven convection system? Which do you think, when you change that reconnection efficiency, what's going to happen to that distance where rotation gives in and reconnection takes over? So if you had a much stronger reconnection, what's going to happen to that distance? Is it going to move in or move out? It'll move in, right? Because what will happen is that it'll affect the flows over a much larger region. It'll dominate over rotation in the larger region. Okay, what if we were to take a planet that over time its spin slows down? One could think of all sorts of reasons for planets' spin to slow down, such as having a moon or interacting with another planet, interacting with the sun. Extrasolar planets are in synchronous orbit with the star, spinning very slowly. What's going to happen to the region dominated by rotation when you turn that spin rate down? It'll get smaller again. You'll be dominated by reconnection. Okay. Okay, so we can look at Earth, Jupiter, and Saturn and calculate this distance. And not surprisingly, when we look at Jupiter, we have a planet that has a strong magnetic field. It's spinning every 10 hours, rapid rotation rate. And indeed, that plasma pores would be many times outside the magnetosphere if you were to do that simple calculation. Saturn, it's not quite so big, but still huge compared with the magnetosphere. Whereas at Earth, we have a plasma pores that is well inside, usually well inside the magnetosphere at a distance of 6 or 7 planetary radii. Okay? So we have a region inside that's dominated by rotation, but around it we have a region that's dominated by these convection fields associated with the solar wind interaction. Now notice we're going to make two big assumptions in doing this very simple calculation. One is that the reconnection drives the solar wind. There could be other ways in which you interact the solar wind with a magnetic field. We come back to what those could be, but keep that in mind. We're assuming it's reconnection. The other thing is we're assuming that the magnetosphere is really coupled well, tightly, to the rotation in that rotation region. And there could be other ways in which that coupling to the rotation breaks down. Not just because it's overwhelmed by the reconnection process, but there could be other processes. Okay, so we'll keep those in mind. Okay, so let's talk a bit about the plasma in these magnetospheres. You'll see that the Earth and Jupiter have similar maximum amounts, a few thousand particles per cc, much less in the outer and the inner magnetospheres. The composition of Uranus, Neptune, and Mercury, I've actually put H plus as protons, but there are also ions associated with ionization and material sputtered off the surface. Is sodium, in fact, the dominant ion, Catherine, would you say? Or is it protons? Depends where you are. Yeah. It is protons. But there are also ions associated with bombarding the surface and sputtering off things like sodium and mercury, and magnesium, the other M metal, right? Yeah, mercury off mercury would be a bit of a handful to handle. Okay, but when we look at Jupiter and Saturn, we have these materials that come from the moons. There's a little bit of nitrogen that comes from Triton, but you'll see that for the other planets, we have stuff coming out of the ionosphere as well as material from the solar wind. When we look at the total source, we can write these numbers in terms of kilograms per second, and you'll see Jupiter and Saturn, it's a little under or around a ton a second. much less of these other magnetospheres. We look at the Earth. This material that's inside the plasma disk is from the ionosphere coming out, but mostly there's a mixture of solar wind and ionospheric material. So we have some material coming in here. The cusp mixes with the material coming out of the polar regions. It gets accelerated and heated in the plasma sheet as it comes in towards down the magnetotail and towards the planet. Another way of showing this, yes?
When you're right that Enceladus and Io as sources will mean sputtering of their surfaces or their atmospheres?
Excellent. It's in fact the atmospheres that a lot of it is just generating neutral material that becomes ionized further away from the moon, rather than particles hitting the surface. In fact, it's harder for the particles to hit the surface because they tend to get deflected around. So most of the stuff is neutrals that become ionized. Okay?
But I think all these satellites have really rarefied atmosphere.
They have relatively, rarefied. They are atmospheres. They are collisional deep down, and so they are atmospheres. Compared with Earth's, they're much less. But they're still atmospheres. Yeah. Enceladus and Triton also has a collisional atmosphere. Okay, but if we look at the Earth, we have this mixture, and in fact there's a whole variety of populations with different energies. So as the plasma becomes out of the polar wind, mixes with solar wind material, comes energized in the plasma sheet, and comes back to form hotter populations in close to the planet. And Norbert Krupp will be talking about ring currents, energetic particles, radiation belts, and so on later in the week, from the energetic particle viewpoint. So we mentioned this issue of energy storage and what's happening. This is from Terry's lecture on last Friday. What's actually happening at the Earth, we're taking kinetic energy from the solar wind, we're storing it as magnetic energy. So you open it up, the reconnection opens up, it carries back the magnetic field, you build up flux in the tail, then you have this conversion of magnetic energy to heat and kinetic energy as you send these bursts of plasma both away down the tail as well as towards the planet. Okay. So this process, sometimes called a substorm, a terminology that's had big fights and battles over the history of the field of magnetospheric science. But basically, again, we're just taking stored energy and converting it into kinetic energy of particles either being ejected down the tail or in towards the planet. And you can look at the signature of dynamics with the Aurora. The Aurora are very useful for giving us a sense of the dynamics. And we can see that this oval of this round region is pretty much maps out the open closed boundary region between closed magnetic flux and open magnetic flux. Notice it's much stronger on the night side. The night side where this plasma sheet is and particles are coming in during these substorms, and that it's highly variable. You've probably all seen these great movies of Aurora going nuts, and we even see once a solar max, we get to see Aurora down here in Boulder, even when you have a large amount of open flux, and so that this auroral boundary moves down in latitude. And the great big storm of 1849, they saw Aurora in Hong Kong or somewhere, right? I mean, absolutely right down near the equator. Okay, so highly variable, but a signature of the processes that are going in the magnetosphere. So let's look at Jupiter. We have a plasma torus, a ton a second of material. We have a 10-degree tilt of the magnetic field, so the plasma that is confined to the equatorial regions, actually by centrifugal forces, it's forced out towards the distant point along the magnetic field, and it is glowing in UV light. This is a movie in UV light, and you can see it wobbling around. The source is about a ton a second, and it's replenished about 20 to 30 days. Okay, so it comes from this moon. There's a flow of plasma around the moon. There's an electrodynamic interaction that leads to strong currents that go to the planet. You'll see the aurora associated with that in a minute. And we have this interaction of plasma with the atmosphere. And the net result is actually not to produce most of the plasma locally. Only about 20% is produced locally. Mostly what you're doing is you're making a big cloud of neutrals that then become ionized, electron impact ionized away from the moon. Now, what happens when you ionize a neutral? Well, the neutral was out there in fairly slow Keplerian orbit, but the flowing plasma is moving, co-rotating with the planet, coming by quite fast. And so as soon as it becomes ionized, electron impact ionized, it begins to see an electric field associated with the plasma motion past it and the local magnetic field. So it begins to gyrate. So the ion begins to gyrate, very large gyro radius, a lot of mass. Remember, these are mass of 32, 16, that sort of masses, times the AMU, so big, heavy ions, little light electrons wiggling. And the energy that leads to heating up this plasma, the ions gain this gyro motion, which effectively heats the ions, comes from coupling this material to the spin. So the source of the energy is the spin of the planet, carried via the magnetic field to the ions and electrons. So in fact, we have a UV emitting torus, all these different lines in the ultraviolet part of the spectrum, and this is a spectrum with wavelength along here. This is actually the Lyman alpha region. This is extreme UV in the 600 angstrom region. You can see little images of the torus wiggling around, right? So these are vertical tori. You can see wiggling with that 10-hour rotation as the spacecraft, the Cassini spacecraft, actually flew past Jupiter, and you can see them getting slightly bigger. At different wavelengths, you see these little images. And you can analyze this to get a sense of the composition and the temperature and the electrodynamics of the physical chemistry of this system, just as you can look at the solar corona and look at the different ions and work out what's going on in terms of the physical chemistry of the solar corona. Very similar sort of physics there. So what's happening when we look at the mass flux? We have a source of sulfur and oxygen as neutrals. It all becomes ionized, makes actually multiple ionization states, single, doubly, triple, even triply ionized material. A lot of it, half of it gets transferred as fast neutral. So you think of this, you've got an ion that's coming along with the plasma speed, and it hits a neutral, it charge exchanges. And so this thing that was moving quite fast now becomes neutralized, and it escapes from Jupiter. It's got escape speed and goes away. That's a fast neutral. It's out of the system, gone. Whereas it creates a new ion that then begins to gyrate and picks up energy from the spinning planet. So this is a way in which you can add energy to the system, but you're not actually adding plasma to the system. For every ion that came in, you have another ion created. There's no change in charge. But it carries away mass. About half of the material is carried away as neutrals. So when we look at the energy flux, about 2 terawatts of energy flows through this torus. We have energy of pickup associated with both ionization and this process of charge exchange. And in fact, somewhere between 40 and 80% of the total energy comes from this process. But those ions are coupled to electrons, and it's these electrons that then excite the ions and make them radiate. Okay, so there's this coupling between the ions and the electrons, and this is via Coulomb collisions of charged particles. So they you can think of, the way I like to think of it, and I had an Italian guy teach me plasma physics. So it's the trucks and the bicycles. And the ions are the trucks, and the electrons are the bicycles. And if you're a cyclist, this gives you a visceral feel for how energy can very easily be exchanged between the trucks and the bicycles. Okay? And so this is done remotely through charge, right? But you know, Coulomb collisions, the trucks of the ions are transferring their energy to the electrons, heating up the electrons, which then excite the radiation. So for the case of the Io torus, 70 to 80% of the energy is just radiated out as UV, and you have electrons. In fact, you also have to add energy directly to the electrons. You have to have a population of hot electrons there. Now, where do they come from? Good question. We don't know. But you ask any plasma physicist how to make hot electrons, and they will say, oh, waves, you know, they say, oh no, I put it in my PIC code and I can make electrons excited to blah, blah, blah. There are hundreds of ways in which plasma physicists can heat electrons. You know, we have parallel electric fields, we have blah, 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 blah. You know, it's easy. These are little bicycles. Easy to excite these little bicycles, either by trucks coming by or by waves pushing them around, okay? It's not known. But it's perhaps not totally surprising that you can add some hot electrons. And you don't need very many, just a fraction of a %, and you can change the amount of energy coming out of the system. Okay, so we've got this torus of plasma. We need to know how it moves through. It's coupled to the planet, so it's rotating. And we have to think about how it moves radially away from the planet. And the answer is, the plasma is confined by the magnetic field. It's going around, so it experiences its inner centrifugal potential. It experiences a centrifugal force wanting to move outwards, but the field is holding it in. But if you have one flux tube A, which has a lot of mass in it, and flux tube B has a little mass, then it will interchange. In the same way that if you have a heavy fluid on top of a light fluid, a small perturbation, and it will turn, it'll turn over. So this is like a Rayleigh-Taylor instability where centrifugal potential replaces gravity, okay? So these will interchange. Now, you can describe this as a diffusive process. You can think of it as being diffusion, and we have a source at Io. How will density vary with distance from the source? So you have a source. Think of a diffusive process. Think of smoke going through a room, or think of ink in a tub of water, or any other diffusive process. Think of people moving through crowds. Okay. So say you have a source of material, right? And so you expect the density to decrease away from the source, right? And so then if you have a very, very steep gradient, then it will move faster, right? And if you have a shallow gradient, you know, it's not in any hurry to move away, right? It's a sort of vague way of describing it. But you can think of this as being, if you have a steep gradient in density, then these flux tubes will interchange more rapidly than if you have a shallow gradient in density. The other point to think about is the fact that if you have a source of plasma, say here at Io, because the centrifugal potential has a direction, just as gravity has a direction, there'll be much more rapid outward transfer of material than the inward transfer of material. And so you'll end up with material moving outwards through the system much more quickly than it moves inwards through this flux tube interchange process. Now I have to show you some auroral movies of Jupiter. They're just so cool. I have to show you this. And we have three kinds of aurora at Jupiter. We have stuff associated with the moons. This is Io, this is Europa and Ganymede. So those moons produce aurora, which is kind of cool. And then we have a main auroral oval, which I'm going to tell you about. And then inside that, we have a small region of variable aurora, which may or may not be associated much with the solar wind. And I've just come back from a meeting where there's a lot of arguments and debates about the source of this polar aurora and where it comes from. But I want you to concentrate when I show you this movie from Hubble of the main auroral oval. So this is taken over a rotation, and of course, because the planet spins and we're looking from Earth, we have to, we've transferred this into a coordinate system that is fixed with Jupiter, okay? And so you can see that viewed from Earth, you have night where it's dark, and then towards us, we see this UV emission from Jupiter's aurora. But sort of look sideways and glaze your eyes a little bit and look for the pattern that you get from this movie of an auroral oval, right? You can see it's a sort of actually more of a kidney bean shape. And that's because there's actually a magnetic anomaly, a little bit of strange field on the side. But you can see it's not like the Earth's auroral that tends to have this big variation. There's not a big asymmetry day-night, and it's actually really pretty constant. But it's fairly thin, and it doesn't vary a whole lot with time. So this main auroral oval, when we average it together, we end up with a pattern like that for the north and a pattern like this for the south. The non-dipolar component of this magnetic field means the North Pole is pointed more towards us than the South Pole. That's the asymmetries. And here's the kidney bean where there's a little bit of an anomaly in here. But the important point is that this main auroral oval is pretty constant, pretty narrow. And it maps to a region that's well inside the magnetosphere. Now, this is important. We're coupling to the planet, and we're coupling to a rotating planet. And so what happens is that as the plasma wants to move out, as it moves out, it will want to conserve angular momentum and slow down. But it's coupled to a spinning planet, and so you will end up driving currents that spin it up and keep it rotating with the planet. And those currents are in the magnetosphere, but coupled to the rotation via field-aligned currents that couple the magnetosphere to the planet. And the aurora are, in fact, signatures of where that coupling begins to break down. So we have azimuthal currents that spread out the magnetosphere. We have radial currents that spin up the plasma disk, and then we have field-aligned currents that couple to the planet. Now, we know that their upward currents are the ones associated with downward electrons. You excite downward electrons. Downward electrons excite the atmosphere, make it glow. That's the aurora. And there must be equivalent downward currents, but we don't really know where those are. Now, there's a complexity here because the main auroral oval shows that these currents are struggling to make the plasma keep rotating. And indeed, the signature of the aurora is where the clutch begins to slip, where the planet is no longer able to enforce rotation. And the big question of our understanding of the giant planets is what causes that decoupling between the spinning planet and the magnetosphere. And it's probably not interference by the Dungy cycle, because that reconnection process is way out near the edges. It's a breakdown somewhere between the plasma sheet and the planet. And this could be a breakdown in the coupling between the thermosphere and the ionosphere. More about this later today. A breakdown in the coupling between the atmosphere and the ionosphere. And a breakdown, there could be a breakdown in coupling between the deep atmosphere and the less tenuous atmosphere above. But what I think is the main factor is that we've barely talked about the fact that you can get parallel electric fields in these plasmas. You always think, oh, MHD, we don't worry about parallel electric fields. But in a region where you have very little plasma, most of the plasma is confined to the equator, you can get a breakdown in these currents. You can't drive the currents, and you end up developing small-scale regions of parallel electric fields where you accelerate ions and electrons in opposite directions. And this is a natural feature of plasmas, which are not often talked about in global descriptions of structures, but you need it to have this breakdown in co-rotation, and we believe it's there. So you will hear this afternoon about the ionosphere as the boundary for these coupling between the planet and the magnetosphere, and there's a lot of stuff going on here in the atmosphere and ionospheric system, and that the situation at Jupiter is that it's this region at about 20 RJ, so that's still only a quarter of the way out to the boundary, where the coupling to the planet begins to break down, and we begin to get these currents that drive the aurora, okay? And how that breakdown happens may be associated with the ionosphere and the thermosphere, or it may be associated with the inability of low-density plasma at high latitudes to carry those currents, and so you end up with these small-scale regions, potential drops, electric fields along the magnetic field that develop, that allow the decoupling between the spinning planet and the magnetosphere. Okay, so I want you to tell me, let me skip on to, I have one question down here, yeah, okay. Pick an object. Pick an object. Why is Mars bold? Mars is bold because we have a mission going to Mars. We, being the University of Colorado at Boulder, we are sending the MAVEN mission to Mars, and Mars doesn't have a magnetic field, so boring little pilly little planet. I'm well known for saying nasty things about Mars, but it's a cool thing. There's all sorts of stuff. We don't know what's going on. We see aurora, we don't understand what causes. Yeah, Mars has aurora. Yeah. We don't know why. It has lost its atmosphere over time. We know electrons bombard and hit the surface in different regions. There's fields that concentrate these electrons that bombard different regions and cause these aurora. And we're sending a spacecraft. It's launched in October. It will go into orbit next year, and it will try and work out, how did Mars lose its atmosphere? Because it doesn't have much of an atmosphere now, you know, and this is obviously very important if you're interested in, you know, were there bugs on Mars? Is there life on Mars now? All these things that you hear about in the news. Space physics is involved, is part of this story. And so the role of the magnetic field is important too. And I think Steve Booker will be talking a lot about this later this week. Okay, and with that, I'm going to end. There's many more planets to talk about, lots of stuff we could have covered another time. Okay. Yes?
Are there any portions of Martian atmosphere permanently protected from solar wind because of the magnetic field?
Yeah. Actually, you know, I have a phrase here. I was thinking about exosolar planets. I have this phrase: the atmosphere basically protects the biota, right? I mean, it's not really the magnetic bubble, the magnetosphere. It's really the atmosphere, right? But the magnetosphere can protect the atmosphere, right? And we think that in the case of Mars, it's the interaction of the solar wind with the atmosphere that leads to the stripping off. But indeed, if there are in fact, there are regions where the magnetic field is sufficiently strong to really push out that interaction region. So yes, in many ways, there are regions on the surface that are more protected than other areas because of the magnetic field. Yeah. Nick?
we're doing nasty things by taking Earth and moving it around and doing nasty things to its magnetosphere. But many of the features that Fran talked about.
Good. Okay. Now I think we have to get on to the homework. Is that right, Carl?